the topic of moment of inertia. So I welcome you once again, and let me remind you that if you have any questions, then please write to me in the comment box, and if you like my channel, then please share and subscribe this. So sometimes you may find a question in this form that we have this rod of length L and its moment of inertia is to be found about this axis. So as I told you that moment of inertia is a property, physical property of the body or material which comes into existence only when the body is having rotational motion. Like force comes into existence when the body is having the linear motion, or the force tries to make the body set into linear motion. Similarly, torque tries to set the body into rotational motion, and then we consider the moment of inertia of the body, and the equation we apply for rotational motion is external torque is equal to I into alpha. Alpha is the angular acceleration. Compare this with external force is equal to mass into acceleration, where A is the linear acceleration. Now suppose I have to rotate this rod about this axis passing through this point at the other end of the rod, and it is to rotate about this. Then for this purpose, at different points I can consider this point, this point, this point, or any other point, how much torque I have to apply for giving it a particular value of angular acceleration. So for that purpose we have to calculate the moment of inertia of this about an axis about which this has to rotate. So generally you will find the moment of inertia of this about this axis. It means that the rotation has to be about this axis. So we will find the moment of inertia first. Let us take a small element of the rod which is from this end, fixed end, is at a distance x, and the length of the element is dx, whereas the rod is having a total length L and mass of the rod is m. So this is point O, suppose A, and we write the perpendicular distance from the axis about which we have to find the moment of inertia in the relation I equal to integral of r square dm. So dm is the mass of this small element and r is this distance. Suppose this angle is theta. So mass density is mass per unit length for the rod. What is the mass of this small element is equal to lambda into dx, or is the moment of inertia of this element about this is r square. So what is r? R is equal to x sine alpha. X sine alpha theta, sorry, you can see in this sine theta is equal to r divided by x. So r is x sine theta, putting the value of dm. So x square sine square theta, theta is a constant here, multiplied by m by l dx. So total moment of inertia about this axis, the constant terms can be taken outside. X is a variable varying from 0 to L. So this is m by L sine square theta into L cube by 3. Integral will be x cube by 3, or ml square by 3 sine square theta. If you find the moment of inertia of a rod about its end point like this, this is the center of mass, the length of the rod is L, the mass of the rod was m, this is center of mass of the rod. Then IO was equal to ml square by 12. Applying the parallel axis theorem, I about A is I about O plus m L by 2 whole square. You will find this as equal to ml square by 3. So Ia is ml square by 3. And if you see this result, this is ml square by 3 into sine square theta. So we have inclined this. In this case, theta is equal to, when the rod becomes in this position, theta is 90 degree. So if you put theta 90 degree, in that case this value and this value, they are same. If you have theta equal to 0 degree, in that case moment of inertia about this axis will be 0. See, rod is in vertical position and you are finding out the moment of inertia about this axis. So why the moment of inertia is 0? The moment of inertia is defined as the product of the distributed mass around an axis about which you have to find out the moment of inertia multiplied by square of the distance, perpendicular distance from that axis. Here mass is distributed around this axis only, and the distribution of mass is such that its distance from the axis is very small, negligible, almost 0. That's why the moment of inertia about this axis is 0. So this is the reason that if you want to rotate a rod like this, take a rod and rotate about this axis, you will have to apply a large amount of torque, means force, multiplied by the distance from the axis or the radius. So you have to apply a large amount of torque, whereas in case you have to rotate it like this about an axis or any other axis, a small amount of torque will give it a large amount of angular acceleration. So you have to remember this result. Now after this, let us find we have this cylinder and the inner and outer radii. This is a hollow cylinder, are A and B, suppose, whereas L is the length of the cylinder, and we have to find the moment of inertia of the cylinder about its axis. So how to do this? If you see it from the top, it will look like this: two concentric circles. This is the axis. The radii are A and B, and let us take a hollow cylindrical element such that the radius of this is R, whereas the thickness is dr. Suppose m is the mass of the cylinder, so mass density is rho is the mass density. In case of the linear objects, we write mass density as lambda, mass per unit length, where in case of solid objects we write this as mass per unit volume, rho, and in case of planar objects sometimes you will find this as rho or sometimes sigma, mass per unit area. This is just what you will find in different books. Different types of notations will be there, so you just have to differentiate. So rho is mass upon its volume, area of cross section multiplied by the length. So what is the mass of this small element? That is equal to mass density into its volume. So mass density multiplied by volume. Now can you tell me what is the volume? Volume of this, that is the area of the base multiplied by the length. What is the area of the base? 2 pi r dr, area of this small elemental ring, multiplied by its length, which is equal to length of the cylinder. So what is the moment of inertia is about the axis passing through its center of mass, r square dm, about this axis. So total moment of inertia is integral of r square dm. Now put the values here. R is the variable here, radius varying from A to B. So I is pi is cancelled, L is cancelled. So this is 2m over B square minus A square integral r cube dr A to B. By 4, or I is m A square plus B square divided by 2. This is the value of moment of inertia of the cylinder. Now see one thing, if you have a solid cylinder, in that case A is equal to 0. So I is m B square divided by 2 which is nothing but the moment of inertia of a disk of same radius. So if you take one disk of radius b, mass of that is equal to m, and find the moment of inertia about the centroidal axis perpendicular to its plane, it will be same as that of a solid cylinder of same mass and same radius. So I told you in the direction of the axis about which you have to find the moment of inertia. So I have this disk, and suppose I have certain number of such disks of radius b, such that the total mass of all the disks is equal to m. Not the mass of one disk is m, total mass will be m. So I put the one disk over other and so on. Or if I divide this into certain number of disks by cutting with the help of a plane which is perpendicular to its axis, total mass remains same. So moment of inertia of all these disks will make the moment of inertia of the cylinder. That means the addition of the mass about the axis does not alter the moment of inertia. So this is how we find the moment of inertia of a cylinder, and we will discuss now further how to find the moment of inertia of a ring and moment of inertia of a disk. First let us find the moment of inertia of a thin ring about this axis passing through its center of mass. O is this point, mass of ring is m, and its radius is suppose r. So we have to find moment of inertia about this axis which is passing through m. What is the mass per unit length? Lambda. This is m by 2 pi r. This is the mass per unit length, and what is the mass of a small element? Let us take this small element and this is subtending. The length of this, let this be equal to dl, and it is subtending a small angle d theta at the center. So dl is r d theta, and mass of this is lambda dl, and di about this axis r square dm. I is integral of r square dm. Now putting the values here, dm is m by 2 pi d theta into r square. Theta is the variable varying from 0 to 2 pi. So these are constant except r, so m r square by 2 pi integral of d theta is theta. By putting the limits, so this is equal to m r square. So if you want to find the moment of inertia about a diameter, we know that symmetrical bodies have same moment of inertia about the diameters, which have circular symmetry like disk, ring, sphere, etc. X-axis, y-axis. So Ix equal to Iy. If you apply the perpendicular axis theorem, IO, this is IO. Ix plus Iy, which is equal to twice of Ix or twice of Iy. So Ix and Iy are same, which is mr square divided by 2. So if I talk about the radius of gyration, IO is mr square equal to mk square. So k here is equal to r. So rotate this ring about this axis by applying some torque, then whole of the mass of the ring is concentrated at its radius. Whereas in this case, if Iy is mr square by 2 equal to mk square, so k here is r by root 2, means 0.7 r approximately. So where is the mass concentrated? It is concentrated at a distance equal to 0.7 r here. Effectively the mass is concentrated. Means if you concentrate the mass of the ring at this point, then the rotation will remain same. This is the meaning of the moment of inertia. And the axis which is passing through the centroid or center of mass of the body and perpendicular to the surface, means surface of this plane of this ring or plane of the disk or any other object, this is called polar axis. And the moment of inertia about this is also known as polar moment of inertia. Now in the books you may also find this written in the form of diameter. So IO is m r is equal to d by 2 whole square m d square divided by 4. So this is how we find the moment of inertia of a ring. Let us find it for a disk. This is a solid disk, the diameter planes, x-axis and y-axis. I have to find its moment of inertia about the axis, which is polar axis passing through centroid. The radius of the disk can be taken equal to r. We have to find the moment of inertia about this. So how will you do? There are different methods available for this. First is by taking a small element of radius r and thickness dr. Here we have to take mass per unit area. M is the mass, m by pi r square. So what is mass of this elemental ring? Sigma into its area, 2 pi r into dr. You can see its surface area is of this ring is 2 pi r into dr. Why it is 2 pi r dr? If you open it, it will form a rectangle. The length is equal to that of circumference, and this is dr. Now this radius, we can write its radius equal to r, capital R. So total moment of inertia, integral of di, that is r square dm. 2m by r square into r dr into r square. R is varying from 0 to r. This is I about the polar axis, IO. mr square by 2. And if you want to find the moment of inertia about x-axis and y-axis, apply the perpendicular axis theorem. These two are equal, so Ix equal to Iy m r square by 4. And the radius of gyration in case of this moment of inertia is r by root 2. That means the moment, the mass of this is distributed here at a distance of r by root 2 from the axis in case of rotation about this axis. This is called the radius of gyration. So this is how you can find the moment of inertia of the disk by using this method. And there are other methods also available. Let us discuss them also. Let us find this by using the method of double integration. So we will find the moment of inertia of the same disk. Moment, the mass is m, so mass density is m by pi r square. In case of planar bodies, we write this as sigma. In case of linear bodies, lambda, mass per unit length. In case of solid bodies, rho, mass per unit volume. But you will invariably find this as rho almost every time in case of planar and solid bodies, so that is immaterial. Just for the sake of the knowledge I am telling you. So now here, let us take this same disk and let us take a small element of this disk, that is a small part of this disk here. It is subtending a very small angle at its center and making an angle theta with the x-axis. The radius of this element is r, this angle is d theta, so this radius is r and its thickness is dr. So I will draw it here separately. This is r and this is dr. This angle is d theta. So the surface area of this small element is, you can almost like treat this as rectangle length into breadth, r d theta dr, and its mass is sigma dA m by pi r square r d theta dr, and the moment of inertia is r square dm. Now here there are two variables, and first let me write what is the value of r. What is r? This is the center of mass. So r is the distance of the axis about which we have to find the moment of inertia, and I am finding the moment of inertia of this about the x-axis. X and y here are same, so I am finding the moment of inertia about the x-axis. Moment of inertia about x and y will be same. So what I should write here in place of r? R is the perpendicular distance of center of mass of the element from the axis. So here center of mass is somewhere at this point. So this is r, this angle is theta. So distance is, if you take this distance, this perpendicular distance, this angle is approximately theta, because actual value of this angle is theta plus d theta divided by 2. This is d theta, this is theta, and this distance you have to find. This is r, this is theta plus d theta by 2. So theta plus d theta by 2 is approximately equal to theta, as d theta is very small. So this distance is r sin theta. So I should write here r sin theta. So Ix is double integral, because there are two variables, m by pi r square sin square theta d theta. Small r is varying from 0 to r, theta is varying from 0 to 2 pi. Now you can perform the integration. So into r d theta. So this will be r into r square, r4 by 4 integral of sin square theta d theta 0 to 2 pi, and sin square theta is, you know that cos 2 theta is 1 minus 2 sin square theta. Mr square by 2 pi into 1 by 2 1 minus cos of 2 theta d theta 0 to pi 2 pi. So this will be equal to so I about x is m r square divided by 4, and this is also equal to Iy. So Io, by applying the perpendicular axis theorem, is mr square by 2, the previous result. This is another method. We have one more method, that is by performing the single integration. Let us take this elementary strip which has the largest length equal to its diameter. When it is moving here, at this point its length is 0. Suppose it is subtending an angle 2 theta at the center, and its distance from, this is x-axis, this is y-axis, from this axis this is y, and this length is x. Parallel to the x-axis, and its radius is r. Now we can find the moment of inertia of this. Its breadth is, you can assume this to be dy. The mass of the disk is m, mass density is m by pi r square, and now we have to find the mass of this small element. So area of this element is x dy. X is the total length, x and y here both are variable, so I can write x equal to, this is r sin theta plus r sin theta, 2r sin theta, and y is r cos theta. So here we will reduce these variables into one variable. So dA is, x is 2r sin theta into dy. What is dy? Minus of r cos theta d theta. So dm is the element of mass of this element, sigma into dA. So minus 2 r square into m by pi r square sigma sin theta cos theta d theta. Now I can find the moment of inertia of this. So we want to find the moment of inertia about the x-axis. So Ix dix is y square dm. X-axis and distance from this axis is y. So y is r cos theta. So minus 2m divided by pi, this will cancel, into sin theta cos theta into y square is r square cos square theta d theta. Here the variable is theta, and we have to integrate this. Here we have made one mistake. Please make a correction. This should be r sin theta. Differential of cos is minus sin. So sin square theta into y square is r square cos square theta. So Ix is integral of this sin square theta cos square theta d theta. Theta is varying from 0 to, you can see here, theta is varying from in this direction to this direction. So I can write this as equal to 0 to pi. It depends upon the direction. It can be a variable from minus pi to 0 also. Now you can perform the integration and find the value. So why we will take the value of theta here from we will take 0 to pi or minus pi to 0. We have a minus sign already. If you take 0 to pi, then you will get the value of I as negative. So that will give you only the numerical value. So theta, we can start from this direction to this direction. The value of theta here is, we are taking in this direction. Theta starts from 0 degree and maximum is 180 degree. 0 is when this strip is in this position. Theta is 0 and theta is maximum is 180 degree. So it depends upon the direction of rotation only. So I will take theta from minus pi to 0. Sorry, pi to 0. So this will be 2m by pi by the property of integration 0 to pi sin square theta cos square theta d theta, and we know that sin 2 theta is 2 sin theta cos theta. So sin square theta cos square theta is sin square 2 theta divided by 4. So 2m by 4 pi 0 to pi sin square 2 theta d theta, and sin 2 theta is 1 minus cos 4 theta divided by 2. Sin square 2 theta is, so this is m over 2 pi 0 to pi 1 minus cos 4 theta divided by 2 d theta. So m divided by 4 pi, and also we should have r square here. So write r square here. So m r square by 4 pi, 2 into 2 4, integral of 1 minus cos 4 theta into pi. So this will be m r square divided by 4. So we are getting the same result. So you can see here there are more than one methods available for finding the moment of inertia of such bodies. Now after this we can find the moment of inertia of another parallel body. Suppose we want to find the moment of inertia of a triangular lamina, that we can also do. We have this triangular lamina. This is any triangle, does not mean that this is isosceles or equilateral triangle. So we can take this as y-axis, this is x-axis. The height of this triangle can be taken equal to h and the base is b. Mass of triangle is m. Let us take a strip which is moving in the direction of y-axis vertically upwards. We will find its moment of inertia and then we will sum up to find the moment of inertia of the entire triangle. Suppose this length is y in the direction of y and breadth is dy. So mass per unit area is m by half bh, 2m by b into h. This is the mass per unit area of the triangle. Now, what is the area of this small element? This is y in this direction. We don't know what is the length. So I drop a perpendicular here on this base. So this one and this one, they are similar triangles. So I can write h divided by y is equal to, this is b and we don't know the value of its base of this ring. Suppose this is equal to L, b by L. L is a variable and y is a variable. Reduce this into one variable. So L is b over h into y. So dA is L dy. So we have reduced this to one variable only, b by h y into dy. So its mass is sigma dA. dm is 2m by h square y dy. And what is the moment of inertia of this about the base or the x-axis? This is equal to y square into dA. So put the value in the equation. Let us make a change here. We should write by the criteria of similarity h divided by height of this triangle. This is h minus y. So h by b is equal to h minus y divided by L. So please make this correction. So from this I can write that L is b h minus y by h. Rest remains same. dA is L dy b into h minus y upon h into dy. So dm is sigma b cancels out and I about x is integral of y square dm, 2m by h square h minus y square dy. Y is varying from 0 to h. So Ix is hy square minus y cube dy. mh square by 6. This is the moment of inertia of this triangle about its base. So you can find the moment of inertia of the triangle about any axis also by applying the parallel axis theorem. So this is all for this discussion. Here we have found the moment of inertia of some planar bodies. So in next discussion we will discuss the moment of inertia of some bodies which have the profile of a particular curve like a parabola, etc. So if you like this discussion, then please subscribe and share, and if you have any questions, then write to me in the comment box. This is all for today. Thank you.